Okay, so this problem says the angular velocity of a rotating rigid body increases from 500 to 1500 revolutions per minute in 2 seconds. What is the angular acceleration of the body? Okay. So 5 omega initial is 500 revolutions per minute, and so this is 500 revolutions divided by 60 seconds. And this velocity is 3 times that, so it'll be 3 times this. So this is 25 revolutions per second. All right, and so assuming constant angular acceleration, you saw this formula. Okay, alpha, the angular acceleration, is omega final minus omega initial divided by t, which is 25 minus 8.33 revolutions per second divided by 120 seconds. .14 revolution per second square. And if you wanted to convert this to radians, 1 revolution is 2 pi radians. Yeah? So 0.14 into 2 pi radians per second square. Okay. And then part B asks you, through what angle does it turn in 120 seconds? So for part B, we could use the following. Omega initial times t plus 1/2 alpha t square. Or also in this case, we could use, since we know the final angular velocity as well, 1/2 omega initial plus omega final times t. Okay, that is the average angular velocity times t. So you could use either one of them. Okay. So let's say we use this one, 8.33 plus 25 revolutions per second times 120 seconds. So it gives you the angle it's rotated through in revolutions. So 2,000 revolutions. Okay. So this thing has rotated 2,000 revolutions in 2 minutes. Yeah. In speeding up. Good. Did you have a question? Okay. a flywheel slows from 600 to 400 revolutions per minute while rotating through 40 revolutions. Yeah. What is the angular acceleration of the flywheel? How much time elapses during the revolution? Okay, so for this guy, you have one of these formulas. Omega final is omega initial square plus 2 alpha theta final minus theta initial. Okay, this is angular velocity as a function of angular position. That's what that equation is. Okay, so we have the final angular velocity, initial angular velocity, and the angle through which it's rotated. Okay, so we'll convert this into revolutions per second. Okay, so omega final is 400 revolutions divided by 60 seconds. All right, so alpha is omega final square minus omega initial square divided by 2 angular displacement. So this is 6.67 square minus 10 square revolution square per second square divided by 2 into 40 revolutions. So alpha so minus 0.69 revolutions per second square. Okay, and if you want to convert it into radians per second square, just multiply that by 2 pi. 1 revolution is 2 pi radians. So minus 4.36 radians per second square. For part B, how much time elapses during this revolution? So you need, okay, we have both the initial angular velocity and final angular velocity. So you can use this formula again if you want. Times time, or okay, now that you have angular acceleration, you could also use this formula. Okay, something that involves time. Okay, so these are both linear guys, so you could use we'll use this formula. Okay, or we can use the top one. Let's use the top one. So time is the angular displacement divided by the average angular velocity. So T is 40 revolutions, 1/2 6.67 plus 10 revolutions per second. Okay, so it took about 5 seconds to go through 40 revolutions. Okay, this problem says a rod of length 20 centimeters has two beads attached to its ends. The rod with beads starts rotating from rest. If the beads are to have a tangential speed of 20 meters per second in 7 seconds, what is the angular acceleration of the rod to achieve this? Okay, so let's say it's rotating like that, and at t equal to 7 seconds, these guys have a tangential speed of v equal to 20 meters per second. And this is 10 centimeters, 0.1 meter. Okay, so these linear speeds are related to angular speed, like v is r omega. And in these formulas where linear speeds are related to angular speed, what are the units for this guy?
Radians per second.
Radians per second. All angles have to be in radians, okay? So omega is v over r, so 20 meters per second divided by 0.1 meter, and so that's 200, 1 over second, and remember the radians is a sort of a free label, okay? So that's the angular speed that you want at the end of 7 seconds, okay? And well, you started off at rest and you achieved this angular speed in 7 seconds. So now we'll go to this formula, omega final equal to omega initial plus alpha times t, and alpha is omega final minus omega initial divided by 7, 200 minus 0 over 7 seconds. Did you guys understand that? So this was rotating the linear, the faster this rotates, the greater its linear speed. Okay, so from the linear speed we can get the angular velocity, and from that we get the acceleration. Okay. This problem says a man stands on a merry-go-round that is rotating at 2.5 radians per second. If the coefficient of static friction between the man's shoes and the merry-go-round is mu s is 0.5, how far from the axis of rotation can he stand without sliding? Okay, so here's a merry-go-round rotating about that axis. Okay. Now this is a top view. Okay. Now if he were right next to the axis, he's not moving, well, he's not going in a circular path, so there's no force needed. Okay. Now, so this guy is going in a circle as the merry-go-round rotates. And what do you need? You need a centripetal force. And where is the centripetal force coming from? The static friction force between his shoe and the floor. Okay. So for instance, if the merry-go-round was made of, let's say, ice, and you were wearing a skating ring, if you spin it, then you'll just fly away straight if there was no friction. Yeah. So the friction force provides that. And now here's a side view of this. Here's the guy. The static friction force is μs times the normal force, and the weight is that. Okay. So the static friction force is, the maximum static friction force is μs times mg. So that's the maximum static friction force. And so the maximum centripetal force is the maximum static friction force, μs times mg. And what is the centripetal force? M, the mass of the guy, times v squared divided by r. And v is related to omega, like that. Okay. So m r squared omega squared divided by r is μs mg. Okay, so you're given this angular velocity. So the furthest you can be is such that this is equal to that. Okay. So the maximum centripetal force corresponds to max for that angular velocity. Okay. All right, so let's copy that. And by the way, the mass cancels. So as long as you're wearing the same shoes, everybody, that's the maximum distance for everybody. μs is 0.5 and g is 9.8 meters per second squared. Omega is 2.5 radians per second. Okay, so you see the second square cancels with that, and what you get is a meter. So R max is okay, so that's the furthest you can stand. 0.78 meters. Okay, so anywhere closer than that, you won't slip. So this says a system of point particles is shown in the following figure. Each particle has mass 0.3 kg and they all lie in the same plane, so they're all in a plane. What is the moment of inertia of the system about the given axis? So the axis is there, it's perpendicular to that plane going through that point. Okay. The moment of inertia is given by this formula, mi ri squared. M is the mass of each particle, and Ri is the distance from the axis of rotation. And you sum over all particles. So the masses are the same, so it's M Ri square. Each particle has that mass, so okay. So the moment of inertia is M and Ri square, 0.2 meters square plus 0.4 square plus 0.6 square. Okay. That's the moment of inertia. If the system rotates at 5 revolutions per second, what is the rotational kinetic energy? Okay. So that's A, B. Rotational kinetic energy is 1/2 I omega square, and omega needs to be in radians per second. Okay. So omega is 5 into 2 pi radians per second. So the kinetic energy is 1/2 0.168. .83 joules. Okay, this shows a system consists of a disk of mass 2 kgs and radius 50 centimeters. So that's the disk, and there is the radius, upon which is mounted an annular cylinder of mass 1 kg. So there is the cylinder. This is mass 1 kg, and inner and outer radius of 20 and 30 centimeters. The system rotates about an axis through the center of the disk, and so the system is rotating about that axis perpendicular to that plane. What is the moment of inertia of the system? Okay. So the moment of inertia of the system is it's the moment of inertia of the ring plus the disk. Yeah. And so for the ring, you can look up the formula. It's 1/2 m r inner radius plus r outer radius squared. Okay. And for the disk, it's 1/2 so I'll write this as 1/2 mass of the ring, mass of the disk, and radius of the disk squared. see for the disk, the inner radius is 0, so it reduces to the outer radius, okay? All right, so let's put these guys in. 1/2 1 kg, 0.2 meters square plus 0.3 meters square plus 1/2 2 kgs, 0.5 meters square, kg meter square. I equal to 0.04, 0.09, 0.13, 0.065 plus 0.25. Okay, so that's the moment of inertia. And B, what is its rotational kinetic energy? Is 1/2 I omega squared. Omega is 10 revolutions per second, which is 10 revolutions per second is 20 pi radians per second. Joules. Okay, 622 joules. All right, so this problem says calculate the torque about the z-axis. So here's the x-axis, y-axis, and the z-axis comes out of the plane of the sheet. Here's how you figure it out. You use your right hand, turn from x to the y-axis, and your thumb points in the direction of the z-axis. Okay, so we use a right-handed coordinate system. A left-handed coordinate system would be x turning to y, that would be z-axis. Okay? So x, y, the z-axis comes out of the plane of the paper. Okay, that is out of the page at the origin. In the following figure, given that F1 equal to 3 newtons, so they're all they're all in the xy plane, the forces, and those are the forces. Okay. All right. So what this is showing you is, see, they show this is perpendicular, so this is the moment arm for force F1. That's the perpendicular, so what you would do is, this component of the force, that's the moment arm, and the perpendicular component would have 0 moment arm. This has 0 moment arm, this force, because it's passing through the origin, and the moment arm for this guy is that, for that component. This component of the force will have 0 moment arm. All right, so to calculate the torque, here the vector formula, okay? But the magnitude of the torque is given by the magnitude of the force times the moment arm. Moment arm is the perpendicular distance, okay? And if a force rotates the object counterclockwise, that's taken to be positive torque. If a force rotates it clockwise, that's taken to be a negative torque, okay? So that is, if use your right hand, if If you're rotating it counterclockwise, that's a positive torque. Clockwise is negative torque. All right, so the net torque is the torque due to force 1 plus torque due to force 2 plus torque due to force 3 plus torque due to force. Okay. This is a clockwise rotation, so that's a negative torque. And F1 is 3 newtons, 3 meters. For F2, again, it's this component of the force. That component of the force gives you 0 torque. So F2 cosine theta, I'll write this F2 cosine 30 times 2 meters. Torque due to force 3, what is this guy? Why is it 0? Yeah, the moment arm is 0. Very good. Okay, so that's 0. And then plus F cosine 20, F4 cosine 20 times 2 meters. And that's minus, that's a clockwise torque. Okay. Minus 9 plus F2 is 2, 4 cosine 30. .46 plus 0 minus F4. Okay, so if this system were starting from rest, which way would it rotate?
Clockwise.
Clockwise. Okay. Okay. A seesaw has length 10 meters and a uniform mass of 10 kgs. So it's 1 kg per meter and is resting at an angle of 30 degrees with respect to the ground. The pivot is located at 6 meters. So this distance is 6 meters, this is 4 meters. Okay. What magnitude of force needs to be applied perpendicular to the seesaw at the raised end so as to allow the seesaw to barely start to rotate? Okay. This guy is 4 kgs, okay, and the force is acting there. This guy is 6 kgs. This guy, little m, is 4 kgs. Capital M is 6 kgs. This is 3 meters, that's 2 meters. And the moment arm is, again, that is 30 degrees. So moment arm is, this is 2 cosine 30. And the moment arm here, this is 3 cosine 30. Okay, so what is it that you want to do? What magnitude of force needs to be applied perpendicular to the seesaw? So what force you need to apply? so to barely start rotating, okay? So what you want to do is, okay, this force is rotating the seesaw clockwise, this is a counterclockwise rotation, and this torque also will be a clockwise rotation. So the net torque needs to be 0 such that it barely starts rotating. Okay. So if you apply a force greater than that, then it'll start rotating like that. Okay. So you want the net torque to be 0, and that's equal to torque due to the mass M, torque due to mass. Yeah. All right. Torque due to the mass M is mg times 3 cosine 30 negative mg times 2 cosine 30, that's positive, plus F times, what is the moment term for the force F?
4 meters.
4 meters. And you want that to be 0. So 6 times 9.8 times 3 cosine 30 minus 4 times 9.8, 2 cosine 30 divided by 4, and that will work out in newtons. So the force you need to apply is 21.2 newtons. All right, we'll stop here.